Okay, how's the microphone today? Is it working in the back? We good? We live? All right, great, thanks. So today's lecture is some advanced topics on concurrency control. We're going to pick up exactly where we left off last Tuesday. I just copied the remaining slides from last Tuesday into this new deck. So anything that was at the back of last Tuesday's deck is either here exactly or it's here in a great deal more detail. Okay? Before I go on, I know that everybody knows that we have a midterm on Thursday. This material will not be on the midterm, okay, which just probably explains why it's kind of a quiet room today, but I'm glad you all came. This lecture is actually a lot of fun. This is the first time I'm teaching a bunch of this material at the undergraduate level, and I think you'll find it actually pretty useful, even though it's traditionally considered advanced topics. The reasons I decided to add this stuff, first of all, are that a lot of people are building new classes of transactional databases these days with new designs for things like very large-scale geo-replicated distributed systems in the internet or for high-performance in-memory databases on single machines. Just there's enough changing in the world of computing that a lot of the conventional wisdom that we learn in the textbook is getting revisited, which means that some of these sort of more advanced ideas may be things you want to draw on as you guys design systems yourselves. And so both as users and as implementers of data infrastructure, I thought a bunch of these topics would be useful. So it's a bit of a laundry list. They don't all necessarily fit together, although you can cross-product most of them. Most of this stuff actually will, in some way, can combine with everything else. But we'll take them one at a time. The first topic will be on lock granularity, and this is something we were going to do regardless. This was in the slides from last time. The second topic we'll look at is how do you get high concurrency within your index data structure, within a B tree? How do you allow multiple readers and writers to coexist? Which turns out to be kind of tricky. And so we'll look at something called a B-link tree, which is a variant of a B tree that allows for high concurrency. And we'll do that in quite a bit of detail today. So there's quite a bit of slides and examples and some pseudocode for that. But the other piece actually of high concurrency with B trees is logical concurrency. There's this spooky thing called phantoms that we'll talk about. And I'll show you how to prevent them using next key locking. All right, so that's going to be kind of index concurrency. And then, I think I promised you last time that there's alternatives to two-phase locking for getting conflict serializability. And so we'll look at one of the other alternatives called multi-version concurrency control. It's an idea that goes way, way back to the 70s, I think, but actually recently has been getting a bunch of attention in a lot of new designs. And it's a very simple, actually, elegant solution to concurrency control. So we'll look at MVCC. Time permitting, today we'll go into distributed concurrency control. So how do you get this stuff to work when you're running on multiple machines? Right? We talked about parallelizing query plans, but we haven't yet talked about how do you deal with locking and all that stuff on distributed systems. And it turns out to be pretty easy, actually, in a sense. So we'll go over that. Finally, if we get to it, and I hope we will, is the notion of weak isolation. Suppose we can have something less than a transaction, something a little bit more mellow, a little bit faster, maybe a little bit easier to implement. What would it be? So we'll look at that. All right, so let's start with this idea of locking granularity. This whole time when we've been talking about reads and writes and requesting locks, we've been getting reads, writes, and locks on things like X and Y. Well, what are X and Y? What are these things we're reading, writing, locking? Well, they could be anything you like because we said our lock tables, you can just put names of objects in them. So in principle, we could lock, say, tables in the database, right? If you want to do something on the emp table, you get a lock on emp. Okay? Why might that be a problem? Why might it be bad to take a lockout on an entire table? Uh-huh. Yeah, absolutely. So, I want to update my bank account. You want to update your bank account. They're both in the same table, but for goodness sake, we're never going to update each other's bank accounts. I don't know who you are, right? So why should I have to wait for you? It doesn't make any sense, really. We'd like to lock at a finer grain than a table. It's too coarse-grained. There's false sharing is one way to think about it. We don't really share that table except as a name for where our tuples go. Okay, great. So let's lock tuples then, right? What might be a problem with locking individual tuples? Yeah. Damn you. Yes, that's exactly it. There's always somebody with the counter argument. So This is totally natural. Suppose you're the person who's like going through all the bank accounts adding interest because you run a job for the bank that touches every single account in that table. So it's going to update exactly as you described. It's going to update every single row. What would be the problem with locking all those rows individually? We can do it, right? Uh-huh. Okay, so you're going to make a lot of calls to that lock manager, which is just going to slow you down. And I will tell you that that CPU cost of going to the lock manager starts to show up at some scale. When you're doing it on every single row, it's pretty costly. It sure would be nice to just call it once and say lock the table, right? There's probably a bigger problem, though, than just the CPU cost. What might that be? Uh-huh. Yeah, that lock table is going to get pretty big, okay? And remember that lock table has to live in kind of some kind of notion of shared memory space for the system. All the threads have to be able to access it. And so you're going to have to allocate a bunch of space that really nobody's benefiting from individually, no individual threads getting benefit for their query, just to hold all these lock requests, all these individual lookups into this hash table, all those lock names. So it's expensive in CPU costs. It's expensive in state. All right, so maybe we should just compromise. Maybe we should just lock something kind of in-betweeny, like maybe pages. But that might not satisfy either of our needs, yeah? So what would be really nice would be able to choose what the lock granularity that's appropriate to the granularity of work we're doing. You want to touch an individual tuple, you should be able to lock a tuple. I want to touch every tuple, I should be able to lock a table, etc. So this is the idea behind multiple granularity locking. And so we just shouldn't have to make this decision for all transactions or even for all actions within transactions. Now, one thing we'll assume in this discussion is that data has sort of Russian doll-style nested containers. All right, so there's a database. We could lock the whole database, after all. Principle. Database contains a bunch of tables. Each table contains a bunch of pages. Each page contains a bunch of tuples. All right, and let's assume that this containment hierarchy holds. We could complicate this. This will work for things that aren't in a pure hierarchy. But for the sake of discussion, let's just assume that it's a containment hierarchy, okay? And the solution to this is going to just introduce a couple of new lock modes to our lock tables, and then a protocol for what order we lock things in. And so the idea is going to be that we're going to take locks at every single level, but some of those locks will be sort of light locks. They won't cost as much. So you always lock from the top down or from the outside in. So you take a lock on the database, and then from there you take a lock on the tables you're going to touch. From there, a lock on the pages you're going to touch, and there, locks on the tuples you're going to touch. Or you can stop earlier in the hierarchy. If you're going to use everything in a table, you'll just stop at the table level. You won't go down any further. We'll see how this works. But you have to lock from the top down or the outside in if you want to think of it that way. All right? And then we're going to have these new locks, which are called intent locks, where you say at an outer level container, or at a higher level in the hierarchy, I'm going to set a lock down below. So I'm going to tell you right now, I intend to do a lock at a lower level. And then you'll actually set the lock further down. So we'll go through an example here in a minute. But the goal is, at some level you stop. And suppose for a moment you're locking tuples. So at that level, you'll actually set real S and X locks on the tuples. But everything above you will have the intent locks that correspond to the locks you actually set at that lowest level. Okay? So IS is a lock you set that says, I intend to get an S lock at a finer granularity than this. So you might take an IS lock on the database and then take an S lock on a table. Or you might take an IS lock on the database, an IS lock on a table, and then take an S lock on a page. Okay? So IS is the intention to, somewhere in a finer grain, set an S lock. IX is the same thing, except you're saying I intend to get an X lock at a finer grain. And then 6 is the combination of I want a shared lock on the entire container and an intent for an exclusive lock on a little piece of it. So if I get a 6 lock on, say, a table, what I'm saying is I want a shared lock on the entire table with an intent to get an exclusive lock, say, on an individual tuple. Okay? Why would you want to have this special 6 mode? Why would that be a common case that we would actually put it together, that I want both S and IX together? Can you think of a scenario where you would want an IX lock at an outer container, knowing that you're eventually, you want an S lock at the outer container, shared lock, knowing that eventually you're going to get an IX lock at a lower level? And it's good to think about tables and tuples. I think those are good levels. So I want an S lock on the table and an IX lock on the table as well. Awesome. Update a tuple only when some predicate holds. So I want an S lock because I'm going to scan the entire table looking for tuples to be updated. And when I see a tuple that needs to be updated, I'm going to need to get an X lock on it, right? So I have an IX lock on the entire table, knowing that I'm going to get some X locks. And then I get the individual X locks on the tuples. But I need the S lock on the whole table because I'm going to scan and read. I'm going to read all the tuples in the table. So S and IX come together quite often when you're doing relational updates, where you say update where predicate. Great. Okay, so let's go through this in a little bit more detail. Each transaction starts from the root of the hierarchy. So if your hierarchy is database table pages tuples, you start at the highest part. If you want to get an S or an IS lock on a node, you have to already have an IS or IX corresponding lock on the parent node. Okay? So you're not allowed to change your mind when you go down the hierarchy. You have to have corresponding intent locks up above. All right? And if you want to get an IS lock, it's okay to have an IX lock above you, because exclusive is obviously more specific than shared, okay? So you can have an IX on the parent. Now suppose that a transaction to get S or IX lock on a node must hold IS or IX on the parent node. Okay, so let's go through a scenario. Over here, I have a table. I'll draw it like this, table T. And I know I'm going to lock some tuples in it later on. So I get to some tuple as I'm scanning through this table. And let's say I want to get an S lock on this tuple. So remember, this is in the hierarchy. This is table tuple. This is a simpler hierarchy than the one over there. I've left out pages. We're not going to do them. I've left out databases. We're not going to do them. We're just not going to set database locks or page locks. So if we're in this thing, suppose I go in and I get a 6 lock on the table. All right, am I allowed to get an S lock on the tuple? Actually, no, because I already have an S lock on the whole table. All right, it would be redundant to get an S lock on the tuple. All right, but am I allowed to get an X lock on the tuple? Yes, because if I have an IX lock on the outer container, which is the table. So I can set X locks down here. Right? All right. Different version. Suppose that on the table I get an IX lock, and I want to get an S lock on the first tuple in the table. All right. Am I allowed to get that S lock here, shared lock? I am, because IX, as it says here, is compatible with S. If you have an IX, you can get if you have an IX, you can get an S on a lower level node. Okay? So that is legal. All right. To get an X or an IX or a 6 on a node, you must have the IX or the 6 on the parent. Right? All right. Finally, last thing, you lock things outer to inner. So first you lock the table, then you lock the tuple. You release in the opposite direction. You release this lock before you release this lock. And that ensures that if two transactions might conflict on something, one of them starting to release, the other one starting to acquire, they will run into each other. Right? You don't want them to release in funny order, so they might sort of race each other. So we always lock top down. We always release bottom up. Okay, and that'll make sure that if there's a conflict between two live transactions, they will see each other as they lock and unlock. All right, so that's the protocol. And the protocol is actually correct in as much as it gives you the same concurrency you'd get as if you locked everything at the lowest level. It's going to give you exactly the same concurrency you'd get by just, in this case, locking tuples, but with a lot less bookkeeping.
What happens if we lock bottom up and release top down?
If you lock bottom up and you release top down, I don't think that works because of the containment hierarchy, right? You'd have to, it would be foolish anyway. You'd say, I will first lock all the tuples, and when I've got all the tuples locked, then I will lock the table. There's sort of almost no point to it. Yeah, so it wouldn't make sense to acquire locks bottom up. And you can't, I see what you're saying. Sorry, so let's take a different scenario. Let's take this offline. This is a little weird. It may make sense. I'm gonna hold this question for a little bit later. The protocol for now, I'll just dictate it to you. You lock top down and you release bottom up. Okay. And I think that makes sense in terms of the granularities. All right, and meanwhile now we have to decide which locks are compatible with which. Remember, IS is an intent to get an S lock at a finer grain. IX is an intent to get an X lock at a finer grain. 6 is an intent lock to get S and IX. And actually, the picture I had up is pretty useful for thinking this through, thinking this lock compatibility table through. So there's table level locks, and there's tuple level locks, okay? And so let's just look at this two-level hierarchy, and let's ask ourselves, if we're trying to take locks at the table level, what would be compatible with what? All right? So this is simple enough because with two levels, by induction, we'll understand how to do it for deeper hierarchies. So we'll just figure it out for a two-level hierarchy. All right. So if one transaction wants an intent to share lock on a table, and the other transaction also wants an intent to share lock on the table, are those compatible? Should IS and IS be compatible? Yes, okay, because there's a scenario where at the leaf level this all makes sense, which is to say at the tuple level in this case. So let's write this down. IS, IX, 6, S, and X, S, X. All right, so we believe that these are compatible. And just to convince ourselves of it, suppose that T1, which will be red, wants a shared lock on a tuple, and T2 wants a shared lock on a tuple. Can they coexist? I want an S, and I want an S. Does that work for tuple level locks? Then it should be allowed for the IS locks. Okay? Great. All right, what about IS and IX? Let's say this is green is T1 and blue is T2, and we're conflicting on the same object. Or sorry, red is T2. We're conflicting on the same object. If T1 wants an IX lock on the table, and T2 wants an IS lock on the table, is it possible at the leaf level that this could work out? Should we allow that to be compatible? I see some yeses and some nos. Why don't somebody who thinks they are compatible give me an example where they might be compatible? Anybody willing to do that? What's the concern with IS and IX for someone who doesn't think they're compatible? What's the concern? Well, shared and exclusive locks are not compatible, right? I mean, fundamentally. So we're concerned that IS and IX locks will conflict a level down anyway when we try to get an S and X lock on the same object. But do they have to be on the same object? They don't, right? So the red guy who wants a shared lock might want this tuple. The green guy who wants an exclusive lock might want a different tuple in the same table, right? So this could work out, which means that from an intent purpose, it's okay for those two intent locks to be compatible. IS is compatible with IX, and we'll sort it out a level down. Okay, so if it turns out they want the same tuple, they'll conflict at the tuple level on this S and X request. Make sense? And if they're on different tuples, they won't conflict, and we did the right thing a level up. All right, so the intent locks are really, they're not protection yet. They're only protection against the case where nothing good could happen below. They save us trouble of going down a level to find out the ground truth. Question? We are. We're trying to get an IS and an IX lock on the same table. So the intent locks are on the same thing. The S and X locks might turn out to be on different sub-things. Got it? And so another way to think about intent locks is they don't actually protect you. They just save you the trouble, potentially, of checking down below because you'll know you have a conflict at a higher granularity. All right? So let's think about this now. Let's skip 6 for a second because it just makes our lives difficult. We know how S and X work out. S is compatible with S, right? So if you want a shared lock on the table and I want a shared lock on the table, that's cool. We know S is not compatible with X, and X is not compatible with X, right? Okay. We're going to skip the 6s for a second. How about IX and IX? Are they compatible? Yeah, by the same argument here, right? If I change this to X, We're still okay, right? So 2IX locks are compatible. That's cool. All right. What about, now let's start mixing our modes. What about shared? I want a shared lock on the table. T1's going to read the whole table. Let's do this. It wants a shared lock on the whole table. And T1 wants T2 wants an exclusive lock on a single tuple. Is that compatible? It is not. There is no way at the tuple level that these two guys could coexist, right? Because they will conflict on this very tuple. Yeah? So one of them has to go first and one of them has to go second. So we might as well, at the intent lock level, say, where were we? IX and S are not compatible. IX and S. I want to get an exclusive lock on an individual tuple. So I'm going to ask for an IX lock, red being I. I'm going to ask for an IX lock up here. Not compatible with this S lock. Does that work out? All right, so we're going to say IX and S not compatible. IX and S not compatible. All right. X and IX, same argument, right? If this was X, it would be all the more so. Yeah? I left my green over here. If I want to exclusively lock everything and you want to exclusively lock something, we will conflict. So those are not compatible. IX and X. IX and X. What's left? S and IS. I want a shared lock on all the tuples, and you want a shared lock on some tuple. It's all shared, right? So that's good. X and IS. I want an exclusive lock on everything. You want a shared lock on something. Yes or no? No. IX and S is a no. We did that one already. IX and S. This is, okay. What about IS and X? Here we go. Did I say that? It's the same difficulty, I think. IS. Oh, no, that's what I just did. Yes, sorry. Yep. IS and X is a no. Good. No. IS and X is a no, which leaves us with 6. So 6 is the conjunction of S and IX. All right, so this should be pretty easy to think through. So let's just do it. I want an intent to shared lock. You want a shared lock and an intent for exclusive lock. Is that okay? Yes, your S and my IS are compatible. Your IX and my IS are compatible. So the whole business is compatible. This guy wants S and IX. This guy wants just IX. Is that compatible? No, because this guy's IX down below will conflict with this guy's S. Right? This guy's getting S and IX on the entire table. S plus IX. So it's going to read everything and it's going to write something. And you want to write something. Well, you can't because he's reading everything, right? So this is no go. 6 and 6. No, for the same argument, right? Your IX conflicts with my S in the same very way we just described, right? You won't be able to get that X lock down below because I have an S lock. So those can't be compatible. 6 and S we did already, didn't we, or did we? We didn't. 6 and S, are they compatible? They're not, because this guy's S conflicts with my IX, right? And then 6 and X certainly aren't compatible. Okay, so check and no. I think we have our compatibility table. You should be able to reproduce this from first principles, just like we just did. And you only need 2 levels of the hierarchy. And just think about these sub-tuples inside this big table if you're ever confused. And remember, the goal is to make sure that at the tuple level alone, would it make any sense? If it can't make any sense at the tuple level, then it doesn't make sense at the table level. Okay? Let's see if I didn't screw up along the way here. Looks about right. 4 across the top, and 2 more scattered in the middle. Yep, looks good. All right, thanks, guys. That was helpful. So that's it. That's multigranularity locking. Take your intent locks as you go down. follow this lock compatibility table. Stop when you get a conflict, right? The lock manager will stop you when you get a conflict. Unlock coming up, and when you're released from your conflict, you go down further until you hit the S or X that you really want. Good? Any questions? All right. There was for a time, I don't know if this is still true, but MySQL, many years ago, when I was asked to evaluate MySQL for an investor in Silicon Valley, and this was early. This was like maybe 2002 or something like that. MySQL eventually was bought by Sun for like $1 billion, so go figure. I don't know anything. I told them not to invest at the time. But one of the reasons, they asked me for a technical evaluation, right? So I started reading the source code, and Query Optimizer didn't exist, and then the documentation had this whole discussion about you don't really want locks because transactions make you slow. Like, look, you're going to have to lock entire tables, and if somebody locks a table, then no one else can even edit a single tuple in that table. It's like, these people have not read Database 101. So you will not have the problem that the MySQL people did in 2002. You are better educated than them. All right, and every commercial database does this, by the way. This is also from the 70s, this stuff. From System R, in fact. All right. So much for lock granularity. Let's move on to a much sort of subtler topic, which is index concurrency. This is really fun. I really think this stuff is fun. I'm excited to be teaching it this year. So there's two issues. There's a structural issue and a logical issue. The structural issue is you're messing with B-tree pages. They're going to split and stuff, right, while you're doing inserts. Now, the insides of the B-tree don't actually hold data. They just route traffic to the data, right? So it kind of would be nice to not have to have two-phase locks on those internal nodes because they're not actually transactional data, okay? And why would it be a bad idea to hold those locks? What would be bad about using two-phase locking on the internals of a B-tree? Yeah. Okay. Right. Every guy is going to go through the root. If you hold an exclusive lock on the root because you're worried you might split it, then no one can do any reads in the B tree, and they're stuck. Right? Even though maybe I'm doing an insert of a tuple way over here and you're doing an insert of a tuple way over there, or a read, I might be worried that my insert's going to split the root, so I exclusive lock the root. And now you can't do any reads at all. So it's essentially table-level locking, which is terrible, right? All right, so we don't want to do table-level locking. If I'm an inserter, should I be worried about splitting the root? I mean, what are the odds? Could I be sure that I won't split the root? It's hard to be sure. Maybe I could be sure. Maybe I could know the capacities of the nodes below me or something like that and know there was enough space that I could release that shared lock, that exclusive lock on the root and kind of go forward. But I'd probably also need to know how many other people are inserting at the same time, because one of us might be the one that breaks the camel's back and splits the root. You can start to see where the thought process goes here. I'd like to not set a lock. How could I be sure that I'm not going to split the root? That thought process is kind of a black hole, actually. It doesn't take you anywhere good. All right? So we're not going to do that. All right? What we are going to do is we're going to set little short locks called latches, where we're going to check some properties of the node, we're going to get comfortable, and we're going to let go of them before the end of the transaction. So we're not going to call those locks to avoid confusion. They're much lighter weight. They're not two-phase locking locks. They're latches. They have nothing to do with the lock table. Just call them latches, right? And they're only in the internals of the database. Only code that runs inside the database, server code, is going to ever set latches. User-level code doesn't know about latches, okay? And so the idea is that we can play some non-serializable tricks with short-term latches on these internal nodes. And that's what the B-link tree that I'm going to show you is going to do. So how can we get the structure to work out even when we're doing fine-grain updates at the leaves? That's what the first problem, right? The second problem is even if the B-tree structure is right, it's actually incomplete, all right? And the key thing to this that's going to sound ridiculous, but we'll see in a minute, is there's no way in the B-tree to lock anything that's in the B-tree that represents data that isn't there. So how do you lock something that hasn't arrived yet? Why would you want to do such a thing? We'll talk about that in a little bit, all right? But there's basically stuff that can't have structure because it doesn't exist yet. And we want to be able to lock that too. So we'll talk about that in a bit. So let me give you a little more detail on latches. What's a latch? Well, before I do it, why do we need them? There are lots of data structures inside the database system, internal data structures, where we've been playing kind of sloppy in our discussions. But there's places where you need mutual exclusion to avoid screwing things up. So remember in the buffer pool, there was a pin count on the pages in the buffer pool? Well, two transactions might want to increment that pin count at the same time. And you can't let them, if it's 3, you can't let them both go, what is it now? It's 3? Okay, now it's 4. Because it should have been 5, right? So it's just an internal data structure inside the database where you had to make sure that it was read-write updated individually one at a time. So it's more like traditional operating systems mutual exclusion. We just have a little variable inside the database, and I want to make sure there's mutual exclusion. So latches are going to let me do this. And we're going to use them in a bunch of places. Pin counts on buffer pages. In the lock table, remember those wait queues? How do you enqueue yourself at the back of the wait queue? You have to get a latch on the wait queue, enqueue yourself, and then unlatch it, and then the next person won't race with you to get in that line. All right, so there's a bunch of places where multiple transactions running concurrently need to coordinate just a little bit, just for a second, on an internal data structure. Latches are for this. And we're going to use them for B+ tree pages. So for all of these, rather than acquiring a lock, we acquire what's called a latch. It is not a two-phase lock because we're not going to hold it till the end of transaction. Okay? And we're also not going to store it in the lock table. It's not going to be in the lock table. It's usually going to be in memory right next to the data structure. It's like a semaphore if you took operating systems class. So right next to that pin count in the buffer pool page, well, actually, the pin count itself in the buffer pool page is the thing that's the latch. And we're going to do a little test and set on that pin count to atomically increment it. All right, for things that aren't counters, pin count's a counter, so you can treat it like a semaphore. But other things like the wait queue in the lock table will have a little indicator variable that says, is anybody enqueuing themselves right now? And you'll do a test and set on that to see if it's 0, and if it's 0, you'll set it to 1, and then you get to enqueue yourself, and then you set it back to 0. Okay? And that little variable, that indicator variable, is going to be a data structure in memory right in that queue data structure. It's not going to be off in the lock table way over here in memory. It's going to be right in the place you're about to operate on in memory. So you get better cache locality in the processor for setting latches. The lock table is a big hash table over here. It's actually kind of expensive to use in CPU cycles. Latches are going to be right where you need them, right with the data that you're about to modify. We will have S and X latches for reads and writes, just like you might with locks, except it's just for latching. All right? And obviously, since we're not following two-phase locking, we're going to have to reason about every single special case where we latch and unlatch things and make sure that we're not screwing stuff up. So it's like, it's the full nightmare of parallel programming, setting latches and unsetting them, right? This is the full responsibility of managing the concurrency of multiple threads in a system. And the only good news is that we wrote the database, the database engineers, and so it's our job to get it right. And that's what we do for a living, and we get paid good money, okay? And we're going to do it once, approximately, and then we're going to call it Oracle, and we're going to be like the third wealthiest guy in the world. Okay, so it's worth it, right? But you're going to have to do it carefully. So today we're going to do it carefully for B trees, okay? And we'll see how it goes. So here's some simple ideas for B+ tree latching. So the simplest idea would be a sort of inductive thing where as the base case you get a latch on the root. Once you get the latch on the root by induction, if you have a latch on some node, then you get a latch on the appropriate child as you're searching down your path. Okay? Because when you have a node latch, you can decide which child to visit, because no one's going to change the page while you're looking at it. And then when you pick the child, you request a latch on it. So this is good. The obvious benefit is that no one will mess with your pages. If you've got all those latches, then you know you've come to the right leaf in the B tree, and no one's going to split the pages you've been on. So if you need to split them, you can. Right? Okay, what's the problem with this? Yes? Yeah, this is the same problem we had before, where we're locking the entire table, essentially, by locking the root. The only good news is we're only doing it for the length of a lookup. We're not doing it for the whole transaction. So it's better than what we had before in terms of the length of time we hold these guys. But locking the root really stinks. What's the worst case scenario? How long might I be holding these latches? You can describe it in some units of cost that we like to use in this class. What's our typical unit of cost in this class, of computing cost? Anybody? An I.O., right? We usually measure things in terms of I.O. costs. So how many I.O.s might we be holding latches through at the root level? I'd argue 3 right? The child of the root, the grandchild, and the great-grandchild, right? For each one of those, we're holding a latch on the root, and for each one of those, we might have to read a page off the disk before we can latch it, all right? Or at least we have to read that page in order to find the child at the next level, right? So IOs in CPU terms take forever, millions of instructions. So if you're holding a latch and you go off and do an IO, oh, that's really, really bad. You just clobbered your CPU concurrency. Millions of instructions could have been done on behalf of other transactions in this table, but you were holding your stupid latch while you were waiting for your IO, all right? This is a very bad thing to do. So we really want to avoid holding a latch while doing an IO when possible, and this is like way too conservative. Okay, and as was pointed out initially, the root's a high-traffic node. Everybody goes through the root, so you certainly don't want to do that. Here's another simple idea. It's called lock coupling, or sometimes it's called crabbing, because you walk down the tree kind of crab-wise. And you can see what's going on in the animation. The base case is you get a latch on the root, and the induction is if you have a latch on node n, figure out what child you need, get a latch on the child, and then let go of your latch on the parent, and then go down the next level. And so you kind of crab your way down the tree. Okay? What's good about this one? Yeah? Nice. Good. All right. So for one thing, we're releasing stuff. So that's good, like the root, for example. And for another, while we're holding a latch, so we know we're getting the real child, we latch the child, and while we're holding the child, we can have a look at it and see if it's safe to unlatch the root. Like maybe there's definitely going to be room on this child for me, so I can unlatch the root. Maybe. Right? We're going to have to be a little bit careful about, well, now we've unlatched the root. We said we were safe here. But maybe now that we've let go of the root, somebody else is going to insert down another path in the parent and split the parent, which could be a problem. So it's not like there's like a solution to all problems, but it does give you the sense that, while you're moving, things are secure, and you don't move again until you know that, like, the next move you're going to make, at least one step, is secure in some sense. We'll just have to get that sense right, okay? But this notion of lock coupling is going to allow us to hold two things true at once that are separated by a potential I/O. But this question of when is it really safe, we haven't really answered yet. All right, I'll just leave it there that it's dangerous to let go of latches still. Can we hold a latch in this case during an I/O? Or do we hold a latch during an I/O? We do, okay? That parent latch is being held while we're doing the I/O to get the child. All right, so we're still latching across IOs, which is bad. We should try to avoid latch coupling if we can. I will accidentally say lock instead of latch today, I'm sure. But I mean latches the whole time, okay? So we should try to avoid latch coupling if we can, but it's certainly better than latching entire paths. All right? Okay, so that was all background. So now you have some tools. Now let's look at the B-link tree. So it's a concurrent B+ tree. And the cool thing about it is readers set no latches at all, which is great because in a lot of cases, reading is the fast path. It's the common case. And these readers will not even go they'll never make a latch call. There's no CPU overhead for concurrency for these guys whatsoever, which seems crazy. How does this work, right? The short answer is, of course they're going to set read locks on tuples in heap files, but they're not going to set any latches in the B tree. So somehow, even though the B tree is changing out from under us, we're going to be able to walk through it and get where we need to get to. All right? And the basic idea is, what's the worst thing that could happen when you're walking down a B tree is that somebody splits the node you're standing on, right? And now it's two nodes. And that's okay. Just move to the second half of that node and keep going. It's kind of the basic idea. Two nodes that just got split from each other are like twins. They used to just be one node. If you take the union of them, they still are sort of one node. So it's okay. It'll work out if we're careful. And so there's really no need to latch on read. You just got to detect when you were standing on a node and it sort of spawned a twin. You need to know that happened. And if it turns out the stuff you were looking for got scooted over, then you need to scoot over. So you need to be able to detect that a node split under you and then decide if the data you really want should be over to your right. Okay? And so basically, the way we're going to do this is, first of all, detection is going to be easy. Every node's going to tell you the largest value underneath it. So when you get to a node, you got there because it was the right thing in the parent. The parent told you to go to that node to find your value v. And if that node says, I've got things up to w less than v, you say, hey, man, where'd this stuff bigger than w between w and v go? Oh, it must have gone over there. Okay? So that high key is going to tell you that you're at a place that got split, and it's no longer got the stuff you want. So that's what the high key is for detecting that a node split in the time between when you read the parent and you got to the node. And then, of course, you need to be able to move to the neighbors. So we're going to have right pointers. Every node's going to point to its sibling to the right at every level of the tree. And that's the basic idea. So nodes are going to be able to split. They will always have a right pointer, so you can always move right. And they will always have a high key to tell you if you're a searcher and your values should actually be to the right, not down, then you go to the right. It's that simple. Okay? Searchers always go down and to the right. The visibility here, we're just going to make sure that the twins are made visible by carefully ordering the rights of them and releasing the latches. And you'll see how splitting works, okay? And latch coupling is actually going to be rare, though it is going to come up. All right? So I'm not going to tell you that B-link trees never latch couple, but they don't do it often, and they never do any latches for reads. Okay, so let's get through it. So here's a B tree we saw in previous lectures. It may look familiar to you. We will turn it into a B-link tree with the wave of a magic wand. Okay. What did we change? Well, internal nodes that are not at the far right have a high key. So you can see that second node, in the leftmost node in the second layer now has a 16 as its high key and a right pointer. It says if you're looking for something bigger than 16, go to the right, because 16 is the highest value in my subtree. And then at the leaf level, we're not going to have bidirectional links. We're only going to have right links. Okay? Of course, the leaf level, you don't need high keys because the data is all there, right? The high key of the leftmost leaf is 3. The high key of the second to leftmost leaf is 8. It's the data, right? There's nothing below them. It is the bottom. So you don't need high keys at the leaves. You just need right pointers. But at the internal nodes, you need a high key and a right pointer for everything but the rightmost node. The rightmost node doesn't need a high key because there's no question of it having been split. It's rightmost. You might need a marker that says it's the rightmost node instead of a high key. Okay? All right, a little notation for the pseudocode we're going to look at. Lowercase variables are pointers to B-link tree pages. Uppercase variables are actual buffers containing a copy of those B-link tree pages. All right? So we're going to have lowercase variables like v or pointer or current. Here's a little subroutine for search that we're going to use in our pseudocode for the B-link tree. It's called scan node, and all it does is it takes an individual node in the tree and decides where to go, either down or to the right. All right, so if the value you're looking for on this node A, which has been copied into memory, if the value you're looking for is less than the high key, actually less than or equal to the high key, that's a bug. That's a bug. Minor bug. Don't let it bother you. Off by 1 errors are acceptable in lecture. We will try not to cause you off by 1 lectures in exam questions as well, because they're not fundamentally very interesting. Come on. All right. If your value is less than or equal to the high key, then do the usual B-tree thing. Return the pointer to the child that is the right child. But if your value is greater than the high key, return the right link. All right. So that's scan node. It's straightforward. It just remind yourself that as you're going through the tree, you may go down, you may go right. And here's the search algorithm. Gratuitously threw a copy of the tree at the top. I'm not sure we need it. But you start at the root. You get a pointer to the root. And you copy the root into a buffer A. And then you traverse down and to the right as needed until you get to a leaf. So while you're not at the leaf, you do scan node to figure out where to go next, which may be down or may be right. And then you copy that pointer that scan node returns into A, into the buffer. And note that copy actually does have to be atomic. You have to latch the buffer pool page while you make this copy. All right, because you don't want the thing you read into A, that page, to be changing while you're copying it. It's got to be a discrete, healthy B-tree page. All right, but that's an in-memory copy from the buffer pool into A. All right, and by the way, there's a variant of all this where you don't do all these copies, but let's just assume we're doing the copies here. All right, now that we've got the right leaf node, well, we don't have the right leaf node. Now that we've arrived at a leaf node, it might have split. And so we have to kind of run down the bottom of the tree to the right till we find the right tuple. So we keep running scan node at the leaf level till we get to a leaf node that has our data or doesn't, right? But that our data is in the range of that leaf node. And once you're at the proper leaf, and you've copied it into A, now it may change after you copy it, but that's okay, all right? Because there's transactions going on here. It's not like going to lose your data, right? Under the covers, there's transactions of the actual data. But if that node has structurally split, that doesn't bother you, actually. That's fine. But if you actually go to that node and you find your value, that's great. And if you don't find your value, you know it doesn't exist, okay? Because you got a correct copy of a leaf node that should have had your value and it wasn't there. Everybody good? So that's reading. No latches were set.
Could you fail between the last get and then give B as
Could you fail? Well, this is the whole point. What could change? It's a good question. So between this last get, which is like 4 lines from the bottom, and the block below it, what bad thing could happen? The worst thing that could happen, the data that you're interested in could not have been deleted or modified, which is to say, by the time you get to that page when you request a lock on the actual data item, that will be managed by transactions. Okay? So there's no worry about the data integrity. There's only worry about the structural integrity of the tree. So what's the worst thing that could have happened to the tree? It could have split. So that node A may, in reality, in the database now be 2 nodes, A1 and A2. But that's fine. They contain the pointers that used to be on A. You've got a copy of it back when it was 1 node. Someone added some stuff. That's cool. Okay? So that's the worst thing that could happen is the structure of the tree changed. I just said that, but I'm dodging slightly. Because I'm dodging phantoms, which we're going to talk about in a minute. The worry is you look and you see that nothing's there, but somebody actually inserted the something. The problem is, how do you get a lock on the fact that the thing isn't there? What does it mean to lock nothing? It's like, I found that 12 is not in the database. I'd like to lock that, please. So we're going to have to deal with that in a minute, okay? But we're going to postpone that issue for a minute. So the only other thing that could happen other than your thing arrived after you looked for it is that the thing split, but you don't really care that it split. Okay. Which is sort of the crux of this whole data structure is you shouldn't care that the structure changed as long as you're seeing its contents. And the content of the actual data is going to be managed by transactions, by long-term read-write locks. Here's an example of what does happen in erase, though. All right, so here's what could happen to you. So here's an example of erase. T1, transaction 1, is searching for 35, and it reads that, in the second layer, it reads that rightmost pointer in the second layer, 2430. T2 comes along to insert 38. It latches, splits, and unlatches that rightmost leaf. All right, T1, after all, was just reading, so it set no latches. T2 raced right past it from the root through that rightmost center second level node to the rightmost third level node, leaf node, inserted a 38 and split it. T1 has already copied 2430 into memory, right? So even if we recursively inserted a pointer to the new child in the parent, T1 doesn't see it because T1 copied an image before then. So T1 is going to arrive at the leaf, and the leaf is going to contain 33, 34, 35, and a right link. And T1 is going to say, oops, bad example. One minor detail. Sorry. This is what I get for doing these late at night. This should just be 38. And this should be 35. And then we're okay. I got my readers and writers mixed up. The reader is looking for 38. The writer is inserting 35. Thank you. So the reader gets to the middle of the tree and pauses. The writer goes all the way to the bottom, inserts 35, splits the leaf. All right. The reader then, T1, gets to the leaf and sees 33, 34, 35 and says, hey, I was looking for 38. Is there a 38? I don't know. Because the highest thing on here is 35. It could be to the right. So I will look to the right. Indeed, there's a 38. Yay. Okay. So that's the worst thing that could happen, is the node you should have got to split underneath you, but you just go right and you find out if it split, and if it did split, you're good. All right, so that's what erase looks like in this context. And the reason you erase is because you make copies of these leaf nodes. I'm sorry, of these tree nodes while you're going, and someone might change them after you've copied them. Right? Question? It says all latches, got to be. If it was locks, then you'd have to hold all your locks to end of transaction. So none of these races could happen, but also you'd get no concurrency.
Oh, so is the biggest difference between latch and lock just the time of the keys?
The most important difference between a latch and a lock is that locks are two-phase and latches are not. Yes, so locks last you until, typically in strict two-phase, till end of transaction. Latches, you can let go of them whenever you want. That's the most important distinction, yes. Okay. So that's reading. Question?
So T2 would latch both the parent and the child?
T2 will latch. We haven't seen. We're going to see the insert protocol in a minute. So let me just hold that thought. But just be aware that T1 set no latches, so it doesn't matter what T2 does. All right, and we'll take it from there. Okay. I put the latch in there kind of for completeness, but we'll see the insertion protocol in just a sec. Everybody good with the reading protocol, though, and what might happen to you as a reader? Worst case scenario, you just move right. Yes? Oh, no, you can be in sort of live lock where people keep getting ahead of you, inserting new stuff. Like someone's bulk loading the tree, and you're like, I'm looking for 17. And they're like, here's 12. And they're like, here's 12. There's another 12. So that could happen infinitely in principle, but it's unlikely to. Okay, yeah. So, but if you're a real jerk, you just keep inserting 12, right, really fast. Yeah. All right. Let's talk about insertions now. Before we talk about insertions, we need another subroutine. All right, it's a latch coupling subroutine, so it should make you nervous. We don't want to call it if we don't have to, but we're going to have to. It's called move right. All right, and it's going to do latch coupling, move right. So you traverse, this is for moving across the leaf level, although I have a feeling it's not just the leaf level. That comment's, I think, misleading. So you're given a value V that you're looking for and a current page that you're pointing to. All right, the first thing you do is you get a latch on the current page, and then you copy that page while it's latched. And then while you've safely got that page latched, you do the scan node thing. And if the scan node thing says, oh, don't go down, go right, well then you latch the right neighbor, so now you've lock coupled. You unlatch the current node, and then you recurse, essentially. Okay. So for some reason, I think my animation screwed up. This is supposed to be a latch coupling animation. Or it went too fast. I was talking while it happened. There it is, latch, release. Right? So it's latch coupling, move right. That's pretty easy. Here's the basics of insertion. You begin by traversing to the leaf without latching. So you're just going to do a typical lookup. But while we're doing it, we're going to keep a stack of where we came from. Because after all, remember, we might have to split back up the tree. It's a B tree. So we're going to build a stack as we go down. Current equals root, copy it into memory so you can look at its pointers. Well, it's not a leaf, recurse through this little while loop. T equals current. Current equals scan node. That tells you whether to go down or right. If current is not right, it's not the link pointer in A, then push T onto the stack S. Right? So basically, you're going to ask scan node where to go next, and if it says down, then you say, good, this node is going to be on the stack. So the stack is going to give you a root to leaf path with no right pointers to the appropriate leaf. Okay? So at the end of this, we've now got, after we do this while loop, we're at a leaf. We've got a stack that is a single stack from the root to a leaf, but we may not be at the correct leaf. And insertion really does need to nail down which leaf it's inserting onto. You can't have splits happen while you're inserting into the leaf node. All right? And so we're going to do move right to latch down the leaf where we're actually going to do our insertion. So we're going to latch couple our way to a leaf. And by the time we pick a leaf that we like, because we're moving left to right, everybody else is also moving left to right, because that's what the protocol does. So no one can race in front of us and latch things in advance of us. Eventually we'll get to a leaf. It'll be the right leaf for us, and we have it latched. All right? And at that point, at the last line of this, we've got our leaf node, and we can do an insertion. All right? And I'll just tell you before we call the do insertion routine, which is a little complicated, if there's room on that leaf, it's a piece of cake. We put the new thing in the leaf, we unlatch it, and we're done. The reason do insertion is complicated is because we may have to split that leaf and then recurse up the tree and blah, 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 blah. All right? But if it's a simple insertion at the leaf level, this is it. You just latch couple across the leaves to make sure that you get to decide that there's room on this page for you to insert your thing. Okay? Questions on this point of it? The messy part's splitting upwards. And so let me just show you a picture of it, and then maybe we'll take a pause. So here's how split works. Here's how it starts. You've got a node latched, and you've got the appropriate place to put it. There's a high key on your node. There's a split key up above, which is probably the same as your high key. Okay? And here's what's going to happen with split. You want to insert something on your node, but there's not enough room, right? So your node is going to need to have a new node. That new node is going to copy your high key and your right pointer. It's going to be the right half of you. Okay? So this leftmost leaf now has got a sort of clone, which is going to be its right half. It copies the high key and the right pointer. And then we figure out the new high key right pointer for the first half of that leaf, right? So now we've got our linked list put together. And then we latch the parent, because we're going to need to insert heart, comma, pointer into the parent. Uh-oh, the parent might have split while we were doing this. Damn it. Right? While we were doing all this nonsense, the parent was not latched. So the parent might have split because one of its other children split, maybe one of its children to the left of us. And so the parent might have split. So when we go up to the parent, we need to get a latch on the parent. That's fine, but the parent may not be the parent anymore. So we call move right on the parent to get to the right level up tree node, I should say. All right, and once we get that, we've got it latched. We can let go of our latch at the lower level. And now we just recurse, inserting heart, comma, pointer into the parent. All right, and then the picture will look the same one level up. Make sense? So you do an insertion, right? How do you do the insertion? Well, if there's not enough room for it, let's just go through this one more time. If there's not enough room for it, you create that split node. You figure out what the internals of it look like. You get a latch on the parent. You find out which parent is the right parent. And then you're done, and you recurse into the parent and do the insertion you want to in the parent. So it's pretty simple. There is some latch coupling here, right? There's the move right latch coupling at the parent level, and there's latch coupling between the child node and the parent level. All right, in the end, everything's good. So this is the insertion algorithm. This is do insertion. And maybe we'll just push through. Yeah, it's 2 more slides. We'll push through, and then we'll take a little break. All right, so what do? We're at the leaf of the tree. We're ready to do our insertion. We assume that we've already got that latch on that child node, which we did before we called do insertion. All right, A equals this. All right, so this is A dot do insertion. So we just wanted to reuse the variable A. So the node we're on is called A. If A has room, do the insertion, write A back into the buffer pool. That's what that put command is, and unlatch it. And then the world can now read that leaf page. Okay, so that's good. It's the case where, there's not enough room on A. We're going to have to split A. So we make a new page, B, and we redistribute it. So we get a pointer to a new page called U. That page is actually in the database. We now copy that page into a variable B. No one else in the world knows about this page but us, by the way. Okay? We redistribute the keys of A over A and B. Y is the new max value on A. All right? We set the high key of B to be the old high key of A. We set the right link of B to the old right link of A. Now we got to create the heart and the red pointer, right? So the new high key of A is Y. The new right link of A is B. We can write B into the database, which nobody knows about it except us. We can write A into the database, which, by the way, we still have latched. Okay? And then we do the recurse up stack to insert Y comma U, which was the heart and the red pointer. All right? And really, old node equals current equals pop, which is that parent. You latch the parent. You do a move right on the parent because it may have split. And when you get the correct node at the parent level, when you're done with move right, then you unlatch that leaf level, which is now called old node, and you recurse. Right, which is just what we went through in the animation. Question? Why do you need to keep the old node latch while you move right a level up? What would be bad if someone split you again while you were trying to insert the pointer to yourself? I think that might be bad. Yeah, that kind of gives me a headache, but we can try. I'll draw you my concern. I won't try to argue that it could be. You may be right, but I doubt it, but you may be right. And I won't try to figure it out on the fly. But here's my concern. Well, it's an invisible concern. Here we go. Here's our leaf level. We just succeeded in splitting it, right? Hooray. This is latched. Here's the parent level. We don't know exactly where at the parent level we're going to have to get to find the true parent. But we start by latching this. And now we're looking for a parent in which to insert a pointer to this guy, right? We're looking for a parent to insert that thing. Suppose we let go of this, and while we're messing around with the parent level, this thing splits again. Now we got two guys running around trying to insert things in the parent level, and I get nervous. Maybe it works out. I'm guessing it doesn't, or it wouldn't have been described this way in the literature, right? But that's the concern. It's basically two people are doing this do insertion routine around the same neighborhood of the tree, trying to insert in the parents at the same time. It kind of does feel like it might work out, maybe. It would take some proofs. You do have to kind of prove this stuff. The crux of all the proofs with the B-link tree, which may work here, are that everything's always going down and to the right. And so there ends up being an order of behaviors, because all of the nodes are monotonically moving down and to the right, and no one can ever race in front of anyone else without racing through them. And so almost all the proofs about correctness here have to do with, well, if you got to this node, that means that there was nobody in front of you going to that node, because everybody would have gone down and to the right through it. Everybody's kind of following the same direction. Splits, by the way, are going up in the opposite direction, and so they run into each other, very much like in our lock granularity arguments. Inserters are going down and to the right, splits are coming up. They will run into each other if they conflict. It's the nature of the proofs. Okay, some details on B-link trees, and then we'll leave the topic. How does deletion work? Well, we're going to make it really easy, all right? So it's going to work just like insertion. So you do the right thing. You get to the leaf level. You do move rights and latch the node you want to delete from. You delete the item in the leaf node, and you unlatch. We're not going to do any space reclamation or any underflow management or anything. So we don't reorganize underflowed leaf nodes. We'll just let them be underflow. And then it's trivial, okay? So that's how we'll do with deletion. And that's usually fine because most trees are not delete heavy. They're usually insert heavy or static. And then there's this thing about latch coupling. There's still latch coupling in here. How bad is the latch coupling? It could be as bad as 3 simultaneous nodes in the worst case. So let's think about it. Move right, we know, is latch coupling of 2, right? So you're holding this and moving right and then letting go. But the problem is you're doing that while you're latching the child. So this is the scenario we just drew, right? You latch the child, and now you want to latch the parent, but to latch the right parent, you're doing move right at the parent level. What is move right doing? It's holding a latch coupling for a second of these two till it lets go of this one. So there's at least 2 and possibly as many as 3 things latched simultaneously. And, it could be happening during I.O., right? Because move right might cost you an I.O. Do you believe that move right will cost you an I.O. in this scenario? Why might you be optimistic that the right neighbor is in memory in the buffer pool? LRU. Is the right node recently used? It's not only recently used, it's recently created, right? If you're moving right, it means that when you were there, it didn't exist. The reason you're moving right is because you were here, you went down there, you did some work. You came back up, you're like, oh, geez, it's split, right? Which means that this thing was created as recently as between the time you visited this guy and the time you visited this guy. So if you believe your parent is recently used, I assure you that things to the right of it are even more recently used because they're the splits-offs of your parent. So they're pretty likely to still be in memory. Your parent's pretty likely to still be in memory, and its right links from splits are even more likely to be in memory. So that's pretty good. If you're worried about it, though, there's various tricks in the literature for saying, geez, the way to avoid latch coupling is you don't actually do the latch coupling until you already try to do it. So what you do is you say, I'm at the leaf level. I want to latch my parent, but I'm not actually going to latch my parent. I'm just going to read my parent. Okay? And that'll force an I.O. So, no, that's not good. That doesn't help because we're still latched down here. So this doesn't happen in B-link trees. But in other trees, basically when you run into a place where you want to do an I.O. while holding a latch, you don't. You let go of your latch. You start over from the root. You just do a read-only version of whatever it is you're going to do to kind of get everything all in memory. And then you start over a third time from the root. And then hopefully by the time you make it to the bottom, everything's already been read. Okay? So you can kind of undo whatever you're doing or stop doing what you're doing, let go of all your latches, start over, and reposition. So it's usually called repositioning because you end up in kind of a different place in the tree after splits. So not B-link trees, but the other popular way to implement this stuff uses that trick. There are ways to avoid latch coupling, which is by starting over and issuing a lot of IOs and then starting again. All right, any questions on B-link trees? They're surprisingly simple, actually. Note that we didn't really have to reason about capacity. Remember our first guess was, when can we let go of that latch on the root? Oh, when we know we're not going to split the root. That actually isn't the way this works. Right? We let go of the root, but we may end up splitting it later anyway. And that's fine. Okay, so it's all about that down and to the right business. That's the winner in B-link trees. It's actually not about capacity estimation. All right, let's take a little break and we'll do one more topic. While we're taking a break, I have a little study guide for you on concurrency control that is traditional to show in this class by now. And if you don't get to watch it now, you can always watch it on YouTube later. It's a classic. I remember when X ran and Y road. There was something so confusing about that race. Basic operations kind of conflicts in the database. When the inline, it's all fine, yeah, it all makes sense. Serious cases alright, you know. Just too slow. It's actually, I found out it's included in a playlist of like computer science songs now on YouTube. There's another one called Find the Longest Path, which is the longest time. It's pretty funny. Wow. I don't think this is funny. I think this is just the introduction to the lecture, unfortunately. Anyway, if you memorize that song, actually, it's got most of what you need to know. It's pretty good. Okay. All right. So here's what we got through. We got through the first two of our topics. I think we actually have time for multi-version concurrency control. And so let's do that, and then we'll probably call it a day. So multi-version concurrency control is an alternative to 2PL. Okay. Oh, no. But before we do that, we have to do phantoms. We'll do phantoms, and we'll call it a day, probably. All right, so this is not multi-version concurrency control. This is the other half of index concurrency. Sorry. Got my outline slides wrong. So we said B-link trees protect concurrency about the structure. They protect us from changes in the shape of the B tree. But they don't address this concurrency on the value domain. And to reinforce the point we had before, suppose you query for sailors. Imagine that. And you're looking for sailors with ratings between 5 and 8 using a B+ tree. All right? And you're going to set tuple level locks down in the heap file. All right? This only comes up, by the way, if you don't do table locking, if you do tuple level locking. So you do that, and meanwhile, I insert a sailor with rating 7. All right? And you do your query again, and oh my God, there's a new sailor that wasn't there before. So you're in a single transaction. You query for all the sailors with ratings between 5 and 8. You see them. There's like 12 of them. And then you come back in the same transaction. You run that same range query again, and there's a new sailor. It's a phantom sailor. It's the phantom sailor of the night. All right? And the problem is that all this theory about serializability actually, with these reads and these writes and all that stuff, assume the database is constant. Right? None of the theory of serializability actually took into account that the database could actually have dynamic values growing. And the System R guys discovered this kind of like by accident. Like, oops. That's why it's called a phantom. They were really like, how did this happen? And so what we kind of want is we want to lock a logical range. That reader wants to say, hey, man, I'm locking 5 through 8. No can insert between 5 and 8. Which sounds okay. But it's like, you say you want to lock between ratings between 5 and 8. And I say I want to lock, like, names between Bob and Claire. And someone else wants to lock on some third dimension. And so what we've got is like this weird hypertope of dimensions. Like you've locked on the ratings dimension, and I've locked on the name dimension, and maybe somebody's locked on 2 of them at once. And so you're trying to lock out like portions of the logical space of all values in the cross product of all your dimensions, and it's a nightmare. All right, so you can't really do this as locking of predicates. It doesn't really work out. It's very difficult to build the lock table that holds those locks. It's actually one of these computational geometry problems in the end, which is why I was describing it that way. You're essentially trying to establish constraints in n space on things that you're not allowed to touch. So it's a mess. So instead, we play a little trick using the index data structure themselves. It's called next key locking. And here's how it works. If you read X, we use the index to find X. And if you don't find X, that's okay. Just lock the next higher item. You search for 7. There was no 7, but you still get a lock. You get a lock at 8. All right? And then if someone is doing an insert or an update, they use the index to find the value. And if the value is not found, they also try to X lock the next higher item. So before I insert 7, I have to get a lock on the next higher thing than 7, which in this case would be 8. And guess what? I run into your read lock. So your read lock effectively locked everything between the key lower than you and the key lower than what you were looking for, and the key higher than what you were looking for. Okay? So effectively, each lock at a value is a range lock. If you lock 8, what you've really succeeded in doing is locking everything bigger than 5 up to and including 8. So we're treating locks in the tree of individual values as locks of a range of values. All right? And another way to say this is that we're using the ordering in the leaves of the tree to partition the value domain into ranges, and then we're locking the tops of those ranges. When you lock an item, you've locked the top of a range. The leaf level of the tree has taken what could be an infinite domain of floats and broken it up into a discrete number of ranges, which is the data boundaries that exist in the database. Right? You get it? It sounds fancy, but it's totally simple. It's just this protocol. Lock the next higher thing. And you'll run into the person who locked it before you. Yes? Yeah, you need some kind of token to lock that's like everything else bigger than that. Yeah, so that's part of the protocol is you have a sort of infinity token. Yeah, and that's a bummer, right? Like, suppose that you don't have very many high values yet, and so you want to lock, suppose you have 1 through 4, and you want to lock 5. When you lock greater than 4, you've locked 4 through infinity, and no one can insert 5, 6, 7, 8, 9, 10, 11, 12, or anything else. So if there's a big range in the tree, including the infinite range to the right, and you need to lock it, you've conservatively locked a really big range. So that's the downside of this. If you have a big gap in the ordering, like 1, 2, 3, 4, 700, and you try to search for 5, you end up locking 700. And now 4 through 700 is completely locked, even though all you were interested in was 5. Okay, so that's the downside of this thing. Is range locking is quite conservative in some cases, where your range is sparse, where your data is sparse in the range, I should say. So that's next key locking. What about if you don't have an index? Then you can't do next key locking. What do you do? It's actually a pretty easy answer to this. What do you do if you don't have the index and you want to lock 5 through 8? Ratings between 5 and 8. Well, remember we started with a query. A reader is looking for 5 through 8. What does that reader do in the absence of an index? What query plan do they use? There's no index, so they scan the heap file, right? And in scanning the heap file, what locks do they have to set? All the locks. They have to lock every tuple in the table or get a table level lock, right? So because there's no index, readers touch everything anyway. So they lock everything. So they might as well lock the table. And once you lock the table, then you don't have to worry about phantoms because no one can insert nothing of any value. Okay? So if there's no index, you're getting table level locks anyhow, and all's good. Right? I'm not even really sure why I have that last line. I'm going to take it out and put in the idea instead. Easy answer here. Okay. MySQL doesn't have phantoms as an advantage of its table level locking protocol. All right. So that's all I'm going to say about phantoms, I think. Oh, yeah, we did that. That was exciting. Yeah, that's it. So here's what we didn't get to, and then I'll let you go. The things we didn't get to and we may never get to, we'll see. We'll see if we have time for these. I'll think about it. Distributed concurrency control. It's actually mostly easy, except for the part that's extra, which is two-phase commit, which is a good thing to know. They teach it in 262, or 162. How many of you learned two-phase commit in 162? Okay, yeah, some of the database material moved into 162. And then weak isolation is a really practical thing. And I guess all I'm going to say about that is I'll give you a little teaser, which is that most database systems, most commercial database systems, when you take them out of the box and turn them on, do not enforce ACID transactions. They enforce something weaker. What, do you ask, do they enforce? Well, some weird weak isolation model that you will never make heads or tails of. And I was going to tell you about kind of what they are. But they're weird. So I guess the headline is be really careful when you turn on one of these databases. It might not be doing serializable transactions by default. Okay? And that seems crazy, but it's true. So maybe we'll talk about that when we have time after the exam. So exam is Thursday. You will get information as to what room to attend, like you did last time. You will get one cheat sheet, like you did last time. Nothing else but your cheat sheet and your writing utensil. Any other logistics information? I don't think so. I wish you all good luck. It's mostly on stuff since midterm 1, but you're responsible for everything because it's all connected. All right. See ya.